On August 25th, 2012, a spacecraft crossed a boundary that no human-made object had ever crossed before, and the instrument reading it sent back did not make sense. Voyager 1 had just left the sun's protective bubble entirely, passing into the space between the stars for the first time in the history of our species, a journey that had begun 35 years earlier as a mission meant to last only a handful of years, visiting nothing farther than Jupiter and Saturn. Scientists expected the magnetic field around the spacecraft to swing around, to point somewhere completely different than it had a moment earlier, proof that the spacecraft had truly left behind everything generated by our own sun and entered a region governed by the wider galaxy instead. That is not what the data showed. The field barely changed direction at all, and for a strange, uncertain stretch of time afterward, that single fact was strange. Enough that some scientists were not even sure Voyager 1 had actually left the solar system yet. This is the story of one of the strangest, most persistent puzzles at the true edge of our solar system, a result so unexpected that when it happened a second time, 6 years later, in a completely different part of the sky, on a different spacecraft, scientists finally had to accept it was not a fluke. It was something real about the structure of the space surrounding all of us, something that suggests our solar system may not be as magnetically isolated from the rest of the galaxy as almost every model built before Voyager actually got there had assumed. To understand why this result mattered so much, you first have to understand what the heliopause is and what scientists expected to find there. The sun does not just emit light and heat. It constantly blows out a stream of charged particles called the solar wind, and that wind carries the sun's own magnetic field outward with it, stretched and twisted by the sun's rotation into a long spiral shape called the Parker spiral that extends far beyond the orbit of every planet in our solar system, curling outward the way water twists off a rotating garden sprinkler. That outflow inflates a vast magnetic bubble around our entire solar system called the heliosphere, a region roughly 100 times wider than the distance from the sun to Earth. Eventually, billions of miles out, the pressure of that solar wind weakens enough that it can no longer push back against the pressure of the interstellar medium, the thin soup of gas, dust, and magnetic fields filling the space between star systems throughout the galaxy. The boundary where that balance tips, where the sun's influence effectively ends and true interstellar space begins, is called the heliopause. Scientists had good reason to expect that crossing the heliopause would look dramatic in the data. Inside the bubble, the magnetic field follows the sun's own rotation, oriented along that long, spiraling Parker pattern. Outside the bubble, in true interstellar space, the magnetic field is shaped by entirely different forces, the ambient magnetic field of the local galaxy itself, built up over the deep history of the Milky Way, with no reason at all to share the sun's particular orientation. Crossing from one to the other, then, should have looked like the needle on a compass swinging to point in a completely new direction. Clear, unambiguous proof, visible in the data the moment it happened, that a spacecraft had physically left one magnetic regime and entered another. Voyager 1's magnetometer told a different story. The strength of the magnetic field did jump noticeably as the spacecraft crossed the boundary, exactly as expected, a real, measurable increase consistent with entering the denser magnetic environment of the interstellar medium. But the direction of that field, the actual angle it was pointing, barely shifted at all. It remained close to the same orientation it had held while Voyager 1 was still deep inside the heliosphere. For an instrument built specifically to detect one of the clearest expected signatures of ever actually leaving the solar system, that was deeply unsettling. Because Voyager 1's plasma instrument, the tool that would have given scientists a second, independent way to confirm the spacecraft had actually crossed into a different kind of space, had failed years earlier and was no longer providing usable data, the magnetic field angle was one of the few direct measurements available. And it appeared to be saying, if you took it at face value, that nothing fundamental had really changed. For a period afterward, this made Voyager 1's crossing genuinely controversial within the scientific community. Some researchers argued the near-identical field direction meant the spacecraft might still be inside some transitional layer of the heliosphere, not truly beyond it yet. It took a separate line of evidence, published in the journal Science in 2013, using Voyager 1's cosmic ray detectors rather than its magnetometer to settle the argument. Those instruments showed a sudden, sharp change, a steep drop in particles known to originate from inside the heliosphere, paired with a sudden rise in high-energy galactic cosmic rays streaming in from outside it, exactly the kind of clean, unambiguous transition scientists had been looking for. Combined with the magnetic field strength increase, this was enough to confirm that Voyager 1 genuinely had left the solar system on August 25th, 2012. But the mystery of the field's direction, the fact that it looked almost the same on both sides of a boundary separating two entirely different magnetic environments, was never fully resolved. It simply sat there, unexplained, a single data point too strange to easily dismiss, but too limited from only one spacecraft at only one location to draw any firm conclusion from. There were two competing explanations on the table, and the difference between them actually matters quite a bit. One possibility was something researchers call draping. Under this idea, the heliosphere acts something like a rock sitting in a moving stream, and the ambient interstellar magnetic field, rather than crossing straight through it, gets bent and stretched around the outside of the bubble as it flows past, the way water curves around a stone. Near the nose of that bubble, the point directly facing the direction the solar system is moving through the galaxy, that draped field could end up oriented in a direction that happens to look deceptively similar to the field just inside the heliopause, purely as a geometric coincidence of how the two bubbles interact, without any deeper physical connection between them. Researchers who modeled this scenario in detail found that along a path running close to that nose direction, a draped field would tend to stay within a single geometric plane as it stretched around the bubble, remaining relatively undistorted, rather than being twisted into a totally different orientation, exactly the kind of coincidental alignment that could fool a single spacecraft into thinking it had found something deeper than simple geometry. The other possibility was something far stranger: magnetic reconnection, a real physical process in which magnetic field lines from two separate sources actually break apart and reconnect with each other, merging the two systems, at least locally, into something closer to a single, linked structure and releasing energy in the process. This is the same basic physical process that drives solar flares on the sun's own surface, and the same process that generates the auroras here on Earth, where our planet's magnetic field lines reconnect with magnetic field lines carried by the solar wind. If something similar was happening at the heliopause, on a much larger scale, it would mean the boundary of our solar system is not a clean, sealed wall separating us from the rest of the galaxy. It would mean our solar system's magnetic environment and the galaxy's magnetic environment are, at least in places, physically connected, actively exchanging energy across the very boundary that is supposed to protect every living thing on Earth from the harsher radiation environment of the wider galaxy. Voyager 1's single data point could not distinguish between these two explanations. A coincidence of geometry at one specific location looks, on paper, exactly like a coincidence of physics, at least when you only have one measurement to examine. What settled the question, or at least moved it meaningfully forward, took another 6 years, and it happened because Voyager 1 was not alone out there after all. Voyager 2 had taken a very different path to get to this point. Launched just weeks before Voyager 1 in August 1977, it used a rare alignment of the outer planets to complete what NASA calls the Grand Tour, becoming the only spacecraft in history to fly past not just Jupiter and Saturn, but Uranus and Neptune as well, before finally turning outward toward the same interstellar boundary its twin had already reached. Dainonang. November 5th, 2018, Voyager 2 crossed its own heliopause, entering interstellar space as the second human-made object in history to do so, at a completely different location along the boundary than its twin, in the opposite hemisphere, at a distance of roughly 119 astronomical units from the Sun, compared to the 121.6 astronomical units where Voyager 1 had made its own crossing 6 years earlier. And Voyager 2 still had something Voyager 1 had lost years before, a fully functioning plasma instrument, giving scientists a direct, independent way to measure the density and flow of charged particles around the spacecraft, rather than relying on cosmic ray detectors and inference alone, the way researchers had been forced to with Voyager 1's crossing. When researchers examined Voyager 2's magnetometer data from its own crossing, published as part of a set of 5 separate research papers released in November 2019, they found the same strange result Voyager 1 had returned 6 years earlier. The magnetic field direction, on the far side of a completely different point along the heliopause, remained close to parallel with the field measured just inside the boundary. NASA's own description of the finding at the time was direct about how significant this was, an observation from Voyager 2 confirming a surprising result first seen by Voyager 1. That, taken alone, could easily have been dismissed as a coincidence tied to a single location, but that now, observed independently at 2 very different points, along the same boundary, looked like a real physical feature of how our solar system actually meets the galaxy around it. That did not mean the 2 crossings were identical, and the differences turned out to matter almost as much as the similarity. Voyager 2 encountered a heliopause that looked, in several ways, nothing like the one Voyager 1 had passed through. Where Voyager 1 found a thick, complicated boundary layer in the region just inside the heliopause, Voyager 2 found something much thinner and simpler, and Voyager 2 detected something Voyager 1 had not: a distinct magnetic barrier sitting in the heliosheath just inside the boundary, a region of notably enhanced magnetic field strength that appeared to play a direct role in regulating how easily cosmic rays from outside could work their way into the heliosphere. 2 spacecraft, launched the same year, using nearly identical instruments, crossing what is supposed to be the same basic kind of boundary, found two meaningfully different physical environments waiting for them on opposite sides of the solar system, and yet both found that same eerie, nearly unchanged magnetic field direction. That combination, same strange alignment, different surrounding conditions, is what eventually let researchers dig deeper into whether reconnection was actually happening and where. A detailed comparison of the two crossings, examining the specific plasma conditions present at each boundary, found that the two locations likely behaved quite differently underneath that shared surface similarity. At Voyager 1's crossing point, closer to what researchers call the nose of the heliosphere, the plasma conditions appeared to actively suppress magnetic reconnection, meaning the aligned field there was more likely the result of draping, the geometric coincidence rather than a true physical merging of the two magnetic systems. But at Voyager 2's crossing point, the magnetic barrier it detected appeared to reduce a key plasma property in a way that could actually favor reconnection happening, locally, right at that specific point along the boundary. In other words, the very same surprising result, two magnetic fields lining up when they should not have, may be happening for two different underlying physical reasons, at two different locations, along the very same boundary of our solar system, a possibility nobody could have even proposed with data from only one crossing. This is precisely why Voyager 1 not being alone out there matters so much to the scientists studying this. A single strange measurement from a single spacecraft can always be waved away as an anomaly, a fluke of instrument calibration, or a coincidence of exactly where and when that one spacecraft happened to cross. It took a second machine, launched the same year, aging in parallel, crossing an entirely different stretch of the same boundary 6 years later, to turn a single strange data point into a real, repeatable feature of the space surrounding our solar system. A feature significant enough to now be actively investigated as evidence that our solar system and the wider galaxy may be linked by genuine magnetic reconnection in at least some locations, even while researchers continue working out exactly where that reconnection happens, how strong it is, and how much energy it actually allows to pass between the two systems. That was not the only strange behavior in the region beyond the heliopause that later needed a second spacecraft to confirm it was real. Starting in 2013, not long after its own crossing, Voyager 1 began detecting specific patterns in the small-scale fluctuations of the magnetic field around it as it moved deeper into interstellar space, fluctuations that shifted in character the farther out the spacecraft traveled, moving from one particular type of magnetic behavior to another as it crossed specific distances from the heliopause. On its own, that too could have been dismissed as something particular to the exact patch of interstellar space Voyager 1 happened to be moving through. Then, after Voyager 2 made its own crossing, in 2018, researchers found the same kind of transition and fluctuation behavior showing up in Voyager 2's data, as well, a separate spacecraft, at a separate location, tracing out a similar pattern of change in the very local interstellar medium as it moved outward. Published in 2020, that result added yet another piece of independent confirmation to the growing case that the region just beyond our solar system is a far more structured, far more dynamic environment than the smooth, largely featureless picture most models had painted before either spacecraft actually arrived there to check. There is a reason this question is not simply an academic curiosity. The heliosphere is often described accurately as a kind of shield, deflecting a significant portion of the high-energy cosmic radiation constantly, streaming in from exploded stars and other violent events elsewhere in the galaxy, radiation that would otherwise reach the inner solar system and Earth at much greater intensity. That shielding effect is not a minor footnote in the history of life on this planet. Over geological timescales, the rate at which high-energy cosmic radiation reaches Earth's atmosphere has real, measurable effects on mutation rates, on atmospheric chemistry, on the radiation exposure. Any future human presence beyond low Earth orbit would need to be protected against. If the boundary of that shield is, in places, more porous and more actively connected to the galaxy outside than the simplest models ever assumed, understanding exactly how and where that connection happens becomes directly relevant to understanding how well protected our solar system actually is, and has been, across the deep timescales that matter for the history of life on this planet. A boundary that occasionally reconnects with the galactic field outside is a meaningfully different kind of shield than one that stays permanently. Cleanly sealed, even if the practical difference in day-to-day radiation levels reaching Earth remains small for now, it also matters for a much more practical, near-term reason. Every model currently used to predict how our heliosphere behaves, how it responds to changes in solar activity, how it might expand or contract over the coming centuries, depends on correctly understanding what is actually happening at its outer boundary. A model built on the assumption of a cleanly sealed, non-reconnecting boundary will make systematically different predictions than one that accounts for genuine magnetic reconnection occurring in specific locations. And Right now, the only real in-place data available to help settle that question comes from exactly 2 aging spacecraft at exactly 2 points along an otherwise unmeasured boundary tens of billions of miles around. Both Voyager 1 and Voyager 2 are still out there right now, still transmitting, still carrying magnetometers that, even after nearly 50 years of continuous operation, remain among the only instruments in history to have ever measured this boundary directly from the inside, rather than inferring it from a telescope pointed outward from Earth. Every additional year either spacecraft keeps sending back data adds another small piece to a question that took 2 entirely separate spacecraft, launched decades before anyone knew this question would even exist, to properly begin answering. It is worth pausing on just how unlikely that timing actually was. Voyager 1 and Voyager 2 were designed in the early 1970s to study Jupiter and Saturn, full stop. Nobody on the original mission team was planning for either spacecraft to still be operational decades later, let alone specifically positioned to cross into interstellar space at 2 different points, along the same boundary 6 years apart, each carrying a magnetometer sturdy enough to still be returning clean data after that much time. If either spacecraft had failed even a few years earlier, if a single component had given out before reaching the heliopause, this entire puzzle might never have existed in a form scientists could actually investigate. There would simply be one strange, unconfirmed measurement, filed away as an oddity, with no way to know whether it meant anything at all. Instead, because both machines happened to survive long enough, in parallel, launched weeks apart on trajectories that would eventually diverge by billions of miles and years of travel time, humanity ended up with something far more valuable than either spacecraft could have provided alone. 2 independent vantage points on the exact same fundamental question, taken from 2 different locations along the true edge of our solar system. Voyager 1 found something that looked at first like it might simply be a strange coincidence at one particular point in space. It took its twin, arriving at a completely different point 6 years later, to prove that it was not a coincidence at all, and to hand scientists an entirely new, still unresolved puzzle about exactly how connected our solar system really is to the vast, magnetized galaxy surrounding it. That puzzle is still open right now, still being worked out by researchers comparing data from 2 spacecraft that have no way of ever returning to check their own work, and no successor currently funded to go back and look more closely at either crossing point again. If this is the kind of story you want more of, subscribe, and let me know in the comments what you think is really happening out at the edge of our solar system.